Hello everyone, my name is Klaus-Dieter. I'm back for the course number on mechanical behavior of materials, number 315008, and we are writing the spring semester 2022. I have given you several approaches, including the stress energy release rate for the propagation of cracks. They had the disadvantage that the theory has a singularity when the radius, the crack tip, goes towards zero. Then we have the stress is going to infinity. And of course, that cannot be. Something will happen at this stress tip, so that we will have some plastic deformation. We have discussed the energy approach of fracture, where Griffiths integrated English stresses to define this energy and the stress energy release rate, and we didn't deal with the details occurring at the tip. So this is the tip here, and what is happening at the tip. The near-tip stress approach deals with the fine details of the stresses at the crack tip. It is associated with the closed form solution of the boundary volume problem in plane stress, plane strain theories, and naturally both approaches converge to the same solution. First of all, let me introduce three crack propagation modes. We have the mode 1, which is shown here, where the displacement is perpendicular to the crack plane. So we have this is the crack opening here at the top, and the propagation and the displacement is just perpendicular to the crack plane, so in the direction we are pulling. Then we have the mode 2. This is the displacement in the plane of the crack and normal to the crack edge, as demonstrated here in the second figure. This is when I stress the two planes a little bit in this shear direction. And then we have this mode where we have shear direction along the Z. So displacement is in the plane of the crack and parallel to the crack edge. That we call mode 3. So note that the mode 1 is the opening mode, so this is crack opening, and mode 2 and 3, they are pure shear modes. This can be remembered here. So we have the person shown in A, and B is ba 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 ba. You just open the mouth. C is crack mode 2 is and D is also again in this figure, which has been displayed already 2 slides ago, we have the mode 1 in blue, the mode 2 in red, and the mode 3 in black color, which is the out of plane shear. The Williamson expansion has been done in 1958, which is a 2D solution only. So we're looking to plane strain and plane stress theories. We have the equilibrium equations. They are noted again here, and the compatibility strain compatibility equation. Then the boundary conditions, we say, if this is theta, we say at the crack, of course, sigma RR at plus minus pi equals 0. So here at this location, sigma RR is 0 because it relaxes at this surface, inner surface of the crack. And the same for the R theta component. So the shear component also becomes 0 in both directions. So if I go plus theta equals pi, or minus theta equals minus pi. Then these equations, they can be reduced and solved, and we get sigma r of r and theta equals sigma r of r and minus theta, and accordingly for the theta components and for the r theta components, because we apply the symmetry here in the mode 1. Symmetry always simplifies problems. Let's assume the stresses to be written in this form. The sigma r equals some lambda, or r to the lambda, times a function of theta. And the same, we write sigma theta theta equals r to the lambda times another function g of theta, and sigma r theta, the shear stresses, we write down as well as a function r to the lambda times h of theta. And lambda can be minus 1/2, 0, 1/2, 1, 3/2, and so on. Then it can be solved to sigma r of r and theta equals some constant a, integration constant a, over square root r times FRR. So we call that now the FGH, we call them FRR, F theta theta, FR theta, different nomenclature, plus some order of r to the 0. So we see it scales with 1 over square root r. And this is for all the three components. They scale, the stress scales with 1 over square root of r. And just to compare it with dislocations, we had something similar, but dislocations, the stresses, they scale with 1 over r, while for the crack tip, it scales with 1 over square root of r. So a little bit less, but still a singularity, meaning the solution doesn't hold at the crack tip, and there must be inelastic regions or plastic deformation region, like in dislocation theory. So this is repeated here again for the sigma r theta theta r thetas, or we can write it down equivalently in Cartesian coordinates xx, yy, xy. And now we define a constant k1 such that a equals k1 over square root of 2 pi, or k1 equals square root 2 pi times a. And then these equations can be written as they are to the bottom, namely sigma xx of r theta equals this function fxx of theta times k1 divided by square root 2 pi divided by square root r. And this k1 is defined as a stress intensity factor, SIF, stress intensity factor, or the amplitude of the singularity. We have the singularity 1 over square root r, and the k1 is the amplitude of the singularity. We also see this 1 over square root 2 pi r is the arc length when we go around. So in a 2D solution, or we only have a 2D solution for the mode 1 near tip stresses, and I like to introduce the K-annulus concept. This equation, sigma yy equals k1 over square root 2 pi r, or 2 pi x, basically scales like the red line here. So qualitatively goes like the red line shown in the graph. If we would do an exact solution, which we can do by finite element methods and so on, we would get something more conservative or more higher stresses at larger distance y from the crack tip here. So this shows you the stress in the y direction and in the distance of the y direction, so basically vertical. Then there's a region where I say in the center the model doesn't hold because we will have plastic deformation. And in the far field the solution, the exact solution, would also be different. But there is a region which fits very well this equation 1 over or k1 divided by 2 pi r or 2 pi x or 2 pi y. And this is like a ring around the crack tip. So if you draw it in 3 dimensions, this is the crack tip, and in this ring 2 pi r, in this region here k, we have this behavior of the equation, and this is where it's critical. Inside it's not described by this elastic theory, and outside we don't care so much because anyway the stresses, they go lower, they go to lower magnitude. So in this ring, which we call an annulus, we want to describe the stresses, and this is then described, approximated by this function k1 divided by 2 pi r. So this is, for example, what may happen inside the annulus. So at small radii there can be dislocation, expanded or emitted into the bulk along this slip plane. So we have a dislocation source here, and this gives you counter stresses which may shield the stresses around the crack tip. All right, let's go back to our continuum theory. We have now the stress intensity factor K, which is a property of the geometry and the loading. So it depends how the system is built up and how you load it. And we have another constant K1C, which is a critical stress intensity factor, and that's a materials property that resists crack initiation. So of course, if the K1 for example, is smaller than K1 critical, then we don't get yielding, we don't get crack initiation and crack propagation. So if we increase now the load or change the geometry, then the crack initiates when the stress intensity factor reaches its critical value. And these K1C, they may be tabulated for various materials, which I show at the end of this lesson. So, now we have crack initiation criteria. We have the K, stress intensity factor, which compares or has to surpass a critical value, K1C. And this we call the toughness. And last time I have introduced the strain energy release rate, SERR, which also is a property of geometry and loading. We call it G. And if that surpasses a critical value, also for this loading mode 1, let's say, then we have another material property that resists crack initiation. So one is a toughness and one is a fracture energy. So how much energy is released when the crack propagates? And the other material constant is how tough the material is. Now what the units of the energy release rate are joule per square meter. It's a rate per area, we said. And the stress intensity factor has the unit megapascal times square root of a meter. Something you have to get used to. So far we have two parameters that describe the behavior of the cracks, namely the K and the G. The K describes the local behavior, namely the tip stresses. So what's happening at the tip is stress tip in the annulus. And the G is the global behavior, energy. You remember when the crack opens in this little ellipse mode, like splitting the mica, then the crack becomes longer and longer, and eventually the momentum becomes less and less, and it stops propagating. Irwin says, for linear elastic materials, these two parameters are uniquely related. And he looks also into crack closure analysis. The work to open the crack is also the work you need to apply to close the crack. So then if we look to the balance, the G1 is the limit A towards 0, du, this was the energy, divided by some crack length delta A times the width, the breadth, but the breadth is constant. And you can work that through and get then for the G1 equals K1 squared divided by the elastic modulus E. This is for plane stress conditions, and for plane strain conditions you get a similar formula decorated with the factor 1 minus nu squared. So we see already the G1 in plane stress is larger than for plane strain, because nu typically is around 0.3, 1/3. So then we have a factor smaller than 1 here. I've shown the stress field near the crack tip for the two plane modes. We have elaborated that. And there's no 3D solution, there's no 3D analytical solution for it, but you can do it in finite element, always. For the pure mode 1, we can write down the stress as sigma 1, 1, sigma 2, 2, sigma 1, 2 shear stress as K1 over square root 2 pi r times cosine theta half. This is a common factor. And then for the 1, 1, you have this component. For the 2, 2, you have that component, comprising sine theta half, sine 3 theta half behavior. I will plot them in a minute. So they are resumed here on this table. I also have here a nice literature which I digged out and which has the advantage that it is online, resuming these tables and some of the concepts I brought. So we have x in this direction, y in the vertical direction. So the force we apply along the y direction in the mode 1, for example. Yeah, plus and minus y we are pulling. And then we get for the sigma xx this expression, those expressions as shown here, sigma x z equals 0 for the plane stress, sigma zz, I have to put my glasses on, and for the plane strain, there's a little sigma zz. For the mode 2, we get according equations which you can look up and plot. And for the mode 3, all these sigma xx, yy, and shear components xy and zz are 0. And we only have shear in the xz and in the yz directions given by those two equations. And then we can write down the displacements by putting here elastic constants. So we have the shear modulus mu, and we have the modulus of elasticity, Young's modulus E. Right, I think this is very much the same thing. Again, nice explanation is given here. And for me, it's more important to imagine what's happening rather than looking too much into the derivation of the formula. So we have here the angular distribution of crack tip stresses for the 3 modes. The rectangular components are left and polar components to the right. So here we have the Cartesian coordinates and here we have the polar coordinates. And note comparable magnitudes of normal and shear components in mode 1 and 2, absence of normal components in mode 3. So normal components in mode 3 are absent. We only have shear components in the FYZ and in the FXZ directions. Yeah, if we look, for example, to Fyy as a function of theta, so as we go around, this is theta, yeah? This is the angle theta, and as we increase this angle theta, or decrease it from minus pi, so minus pi is here to plus pi is there, we go around this crack tip here, then we see the Fyy becomes maximum, not at 0, but in some orientation here, maybe 30 degree, at plus and minus 30 degree. That means the Fyy becomes maximum in those direction. We said already when we are plus and minus pi, it has to be the free surface, this little blue thing here, and the free surface has the stress boundary condition 0. So that was our boundary condition. Fxx is maximum in the forward direction, so in the crack propagation direction. And the shear stresses here, they are asymmetric. We see that the normal stresses Fyy and Ffxx, they are symmetric with respect to going in the positive and the negative angular azimuthal direction. And of course the shear stresses, they are asymmetric because you just change the sign as you go around. Or you can plot the same thing in polar coordinates. So we have the FRR, the radial stress, the hoop stress, and the shear stress. The hoop stress also becomes largest in the x direction, so in the x forward direction around theta equals 0. FRR has again two maxima which are off the forward direction by a certain angle. And that may be interesting. So for mode 2, we can get a similar formula. So mode 2 is, of course, we shear now along in this plane, along the x direction, and therefore the normal stresses become asymmetric if you go from the top to the bottom, but the shear stresses become symmetric. And in mode 3, we have absence of normal stresses. We only have xyz and fxz. And this is because if we shear like this, we only go shear between the x and the z. So we always get a z component, while the shear in the xy component is symmetric and therefore becomes 0. Again, this is resumed here. Stress fields ahead a crack tip in polar coordinate system. Now, let's look to the fracture in metals as a function of thickness. When we do cracking experiment, we can have either a thin plate where the breadth B is small, can be medium, and it can be thick. So typically we have two cases. We have a thin case and we have a thick case. Of course, if B becomes very thin, then we have our plane stress situation, which I introduced in the theory of elasticity. Here we don't care about the thickness. It is constant. The stresses are constant over the thickness B when B becomes very thin. And obviously, as B becomes thick, a meter thick or infinity, then we have the plane strain situation. And then, of course, there's a transition zone between B, between very thin and very thick, and that we call medium. So we get here the plane stress fracture. Here we get the plane strain fracture. And here we get a mixed mode of fracture in the medium constellation. So plane stress fracture, we have basically, when plane stress, we take a plate, and we know already the Schmidt factor is highest in the 45-degree direction. So we get slip in the 45-degree direction and shear bands in the 45-degree direction. And the same symmetric 45-degree direction can be in the other. So eventually they grow from the surface in here, they grow from the surface in there, and they meet. So you can get a fracture surface which looks like that, 45 degree, and eventually they meet, and you get these lips. We call these items, these triangles, we get the lip. So in plane stress situation. Of course, if you have plane strain, then there is not this symmetry and the surface. You don't have this free surface because the surface is far away, is shielded off by the other stress and plastic deformation fields. Then you also only can crack in the plane strain. You only can crack here, horizontal. You just pull the material apart. You just peel it apart. And that gives you the plane strain fracture surface. So for plane stress, they're inclined. For plane strain, they're horizontal, parallel to the crack propagation vector. And the mixed mode is we have in the center some flat area and these lips at the border where we go to the plane stress situation. So the K critical goes down from the plane stress to the plane strain. Here, for example, if we look to the G1, the SERR, I remind you that we have, for the plane strain, we have the factor 1 minus nu squared with respect to the plane stress. So plane stress situation is larger than the plane strain situation. And therefore we can have a larger K critical, which is large here at small thicknesses, and as thickness grows we go to a asymptotic value K1 critical. So what does it mean for the two situations, plane stress here and plane strain? In plane stress we have, or both situations, we have sigma 11 equals sigma 22 equals K1 divided by 2 pi x1, and for plane stress now we have sigma 33 equals 0, while for plane strain we have epsilon 33 equals 0, and therefore sigma 33 equals nu times sigma 11 plus sigma 22, which is approximately also K1 or proportional to K1 over 2 pi x1. So the difference basically between the plane stress is here the ZZ component. Here we have 0, and here it's approximately K1 over 2 pi x1. As we have now the two stress tensors for plane stress and plane strain, we can calculate, for example, the von Mises or the Tresca yielding criteria. And if we, in this case, calculate von Mises, apply von Mises, you can do all the exercise. And looking for the plane strain solution, then we get this inner figure. While for plane stress, we get this outer figure, which is larger than the inner figure. So, as we now look as a thickness through the plate, so this is from one surface of the plate to the other surface of the plate, along the crack tip, which goes through the breadth B, so this is B here, then we have this plane strain solution, which is smaller than the plane stress solution at the surface. At the surface, we have a region of plane stress. Then in the thickness, we have the region of plane strain. And at the other surface, we get the region of plane stress again. So this is the yield surface. And in between we have a transition zone which is not really described by our equation, but which can be interpolated. So for the plastic zone size, in the first approximation we have sigma yy equals K1 over 2 pi r square root, and sigma yy we call it, if sigma yy becomes the yield stress, sigma y, then K1 equals K1c, and let R be a plastic zone, Rp. Then Rp, the plastic zone, which is shown here, becomes approximately 1 over 2 pi times K1c over sigma yield to the square. So this will be the size of the yielded redistributed stress. In that figure here, we have here the theoretical elastic stress, the dashed line, but then we get the plastic zone, so we get yielding in this plastic zone, and then the stress redistributes. That means it remains constant at about the yield limit, and then it yields more and more and more when it surpasses, so the yield surface also goes a little bit into the material, so along the x direction, and then it becomes weaker. If you now look in the first approximation to the plastic zone size, then again sigma yy is shown here, the same equations as before, and we get the radius of the yield sphere here is approximately 1 over 2 pi k squared over sigma yield squared, and for the plane strain we get a 1/6. Otherwise everything the same. So we see here we have 1/2 and there's 1/6. That means the plane stress yield volume is about, the radius is about 3 times larger than for the plane strain situation. This is the important takeaway message. So I come back to this figure. That means we have here the inner figure for, I think it's for Mises criterion, and this is 1/3 about the figure and the plastic yield area of the plane stress at the surface. Here again in the cross section, so in the center here of far away from the surface, we get the plane strain, and here we get the plane stress, and there's approximately a factor of 3 between them. The crack tip deformation patterns. So in A, where we have a plane stress, so this is B is thin, it's small, then I mentioned already we get these 45-degree shear bands, because the Schmidt factor is largest under 45 degree. So we find a lot of crystal planes, small crystal planes, who have a good Schmidt factor there, and that gives the so-called shear band, and we get slip along this direction and here along the other direction. So if you put that together, if it cracks, eventually we may get a lip here at one of the edges, either to the top or to the bottom. Depends which one initiates first. It's a crack nucleation and then growth process. So there are always some statistics inside. However, if B becomes very large, then it cannot shear in this direction, because we're looking to something in the volume here which is far away from the surface. So we have the component which goes from top left to the bottom right, and from the top right to the bottom left. And if you put those components together, they become horizontal, symmetric components with respect to the y direction here. So it has to be symmetric to y, so kind of a mirror plane, left and right. So we get this horizontal or crack propagation, which is parallel to or perpendicular to the y-axis. This figure compares the von Mises and the Tresca yield criteria for the application to the plastic zone shapes. And we have here to the left the situation von Mises, which I've shown before. For both, we have the plane strain, which is inside this curve here, this dongle, and the plane stress, which is that curve a little larger than the plane strain. Now just let's look to the plane strain situation under von Mises and Tresca. So this little dongle is magnified here. You see 1.5 is here, 1.5 is there. So it's the same curve as the inner plane strain curve. Recopied to that figure, magnified von Mises. And we have then in comparison the Tresca criterion. With the Tresca criterion, this plastic zone shape is smaller and more forward oriented. So in fracture, we have the plane strain fracture toughness, which is given by the constant Chi1 critical, and this is for thick plates. For thin plates, we have to look to the plane strain fracture toughness, which is a rather complex property. And now thickness effect is seen for brittle materials such as ceramics and glasses, because then there's no plastic zone, as we know, and the fracture occurs immediately. So what happens as a function of delta A or crack propagation for idle brittle materials? We have in ceramics and glass, we have the K1C or the G1C. They're just constant as a function of delta A. So if A grows by delta A, there's no change of the K and the G's. So there's no additional energy consumption mechanisms. For metals, we know metals are ductile, so we have additional major energy consumption mechanisms, such as plasticity by dislocation emissions, and that depends upon the geometry, the thickness, and so on, and it must be considered very carefully, because each metal is different, the mechanisms are different. So there are various situations. If this is the initial crack and we grow it, if there's energy consumption, so we have G1 critical starts here, and then we have energy consumption, so we call this GSS. Then we can see that the critical GC increases as a function of delta A, and that means if we are in this region, we increase by delta A, the G increases also, the G critical also increases together with delta A, so it may not grow. It will not grow because I consume more energy to grow the crack rather than winning energy by the stress release. And that goes to a maximum. So eventually, if I get to this horizontal tangent, then it doesn't matter anymore. I can grow the crack by delta A, but G does not increase anymore, so it grows and grows and grows, and that's the situation for the brittle material, for the glass, which is just a horizontal constant line. And here some of the mechanisms. So for small increase we get blunting. This is just a small plastic zone here. Then we have where the GIC is stable. So the GC in the stable condition, that means I get a plastic zone, and the plastic zone is there, and the crack grows by this length, but it is within the plastic zone, so it will not grow further. But if the plastic zone is smaller or reaches the size of the length of the crack, so the crack goes through the whole plastic zone, I come here in a zone which is undeformed, and then it just goes and cracks, propagates and becomes unstable. Welcome back after the break. Because it's so important, I like to go over this last chapter again. So what happens after the crack initiation is very critical in the design. For idle brittle materials, we have this behavior as shown already, namely when the crack grows with delta A here on the horizontal axis, the stress intensity factor and the strain energy release rate, they keep constant as a function of delta A. This is not so in metals, because in metals we have the effects here. We have this plastic zone, so we have the blunting, we have the stable and unstable conditions depending whether the plastic zone grows faster than the crack or whether the crack grows faster than the plastic zone. So in the brittle material, of course, the plastic zone is very small and the crack grows faster. In metals, it may be the other way around, so we get plastic deformation, and therefore the G can increase as a function of delta A. And only when it becomes then horizontal, when this curve becomes horizontal, then we have the crack propagation like in the brittle material. So I introduce here the material's resistance to fracture, which is also called the R curve, the Griffith's instability criterion. You can find this in the textbook, and it tells failure should occur when the rate of change in the elastic energy rate dG over dA equals the rate of change in material resistance to R, then crack growth occurs. We see that here we have this materials resistance to fracture curve, the R curve, this bent curve in the figure, and then we have the energy release rate G, and when the tangent is equal to the R curve, then we get into the instability that crack can propagate. So the material's resistance to fracture R is expected to increase with increasing plastic zone development and strain hardening. We talked about strain and stress hardening processes in different chapters, for example in the dislocation chapter, work hardening. So both G and R increase with increasing stress level. And when they have the tangent, the equal slope, dG over dA equals dR over dA, as shown there as well in the figure caption, then we get the instability. In the textbook it is explained how you can measure this with experiments. You can calculate such R curves, but you also can measure them, and by applying different energy release rates. And experimentally through cracking, you have this impact testing. You have had that in the lab, and from that you can calculate the curve. So I just refer to the textbook because of the limited amount of time we have. I have to rush through the coming slides. What you basically do, you set up your experiment with different G. As I said, G depends on the geometry of the experiment, on the geometry of the loading. So you set it up differently. You get different slopes here. And then for each slope, you can find the tangent and you get the line. You can then construct the line, which is called the R curve, as shown here. So there's a little bit of literature. This is really referring to the textbook. Also, now how to evaluate the K1C, the critical stress intensity factor for mode 1. This is tabulated, and this is also explained in the ASTM E399 guidelines, standards on linear elastic plane strain fracture toughness K1C of metallic materials. And there's one page out of this standard book. I think it's by ASM. So they give you all the geometries, how to make test samples, how to make the specimens, how to design an initial crack. So you have an initial crack here, and then you have a crack propagation, dA as a function of A. So this is the load here. So you load here in these two holes. You put a tensile stress on. This is the lever arm A. And you do the various experiments according to those descriptions. You have done that in the lab. You apply different loads, sigma yy, and eventually you can work out the R curve. These are the standard test methods for linear plastic strain fracture toughness in metallic materials. So there are a few pages. Here we have practical numbers. So we have the metals, we have the ceramics, and we have the polymers. And you see the K1C, they range between 65, maybe 30s, 20s, 30s. For the weaker aluminium, megapascal per square root of meter. And for the steels, you get the higher values. Ceramics is 1 order of magnitude lower, 1 or 2 orders of magnitude lower. We see cement, concrete is 0.2, magnesium oxide is 3, and aluminium oxide, alumina with 50% zirconium oxide is 10. So metals, they go from the hundreds down to the tens. Ceramics 1 order of magnitude lower, so 10 to 0 point something. And then we have the polymers. And the polymers, they are even weaker than the ceramics, typically shown there, between 0.3, maybe comparable. You have good polymers nowadays, and I always say you have to stop polymer samples when you cannot open the plastic bag with your foot inside anymore. Another table, just to put everything together. Steel is very high, G1C, critical, and the K1C is 150. The elastic modulus is 210 to compare it. Aluminium alloy, the numbers are lower, as shown here. And you can go through the table. There are many tables now coming on the following slides, which are compiled for you. So if you need the one or other material, you just look it up in the tables. Also for single crystal here, this is fracture surface energy of sapphire at room temperature. So that's in the 001 plane, so it's a hexagonal system, and the basal plane, it's larger than 40, but you see in the other directions, in the other planes, it's much weaker, particularly in the pyramidal and in the prismatic planes. Here we have plane strain fracture toughness of some polymers in air. So you see this epoxy, it's not so strong. Then we have polyethylene that can go up to 5 megapascal per square root meter. Again, the metals they are shown there. I can repeat that many times now, that's why I rush through the slides. Metals and alloys, as shown here to the left top, they have very high fracture toughness. So the K1C is, as I said already, can be higher than 100, can be 200, 300. Then we have the magnesium alloys at the lower end of the metals, aluminum and titanium alloys in between. We have graphite, ceramics, semiconductors, diamond, that's your favorite semiconductor, I guess, for the ladies. And they are 1 order of magnitude lower than the metals, as said already, or even 2 orders of magnitudes lower, like concrete, silicon, and glass. Polymers, they are comparable, they overlap with the ceramics and the blue shaded ones. And then we have the composites. So composites, they are materials with one material together with another material in layered version or somehow dispersed versions. And you can have fracture toughness as high as in steel, like here for the carbon and the carbon fibers, and others are shown here. So it's a relatively broad range, over 1.5 orders of magnitude. So based on the table, the metals, they have the highest fracture toughness, then we have the composite materials, and then we have the ceramics and the polymers in a similar level. Another example, epoxy. We have seen epoxy is not so tough. It's relatively weak, but when it's modified with rubber, so you make a composite, then it increases at least by a factor of 2 at low temperature. At low temperature, maybe the rubber also becomes brittle, but then rubber becomes very ductile and very elastic. We know that at higher temperature. So the rubber particles, they may take some of the load in the crack propagation of the epoxy, so that it becomes much tougher. Another diagram here with applied stresses and the K1C for different alloys. So we have the aluminum alloys at the bottom left, lightweight, but toughness and hard stress, yield stress are not so high. Then the titanium alloys, they perform much better. So they're very tough, they're as tough as steels. Some of the titanium alloys, some of the modern titanium alloys. So it really depends what you do. You know, iron, steel is iron. It's also not so tough. But if you go to steels, like high-strength steels and Mar-aging steels, then they become very tough and very high-strength steel, so the HSS steels. Last not least, I want to mention that you have to design in the engineering the workpiece with cracks. So airplane has cracks, a car has cracks, a train has cracks, everything has cracks already. So you have to design with cracks, because you know there are always inclusion, there's always something, and you have to design for allowed stresses to prevent catastrophic failure during the service. That's why you check the car, and that's why you check the airplane. Sometimes you check for cracks. If they are over a certain length, then you say you need to replace that part. You have to service the part. Otherwise, if it's under a certain length, which you can calculate with a margin, then you just continue flying and operating it. So, design with cracks, it's very important, of course, in the aerospace industries. In other industries, your mobile phone may have some chips inside, and you drop your mobile phone on the floor, and there are huge stresses acting on these solder points, on these thin wires. So the wires, they are just a few micrometers thick, like your hair, or maybe even thinner, and the cross section is not very, very big, and therefore the stresses may be huge. Or here, this catastrophic failure. If you can read the caption, then we may work out maybe where this have happened before. So I didn't look it up either. So, what is the K1 of a cracked body? We have had that in the Griffith plate with the small crack. The K1 has been the sigma square root pi a. And then we have a geometrical factor. We can just add, engineer just would add a geometrical factor, beta, in front of this term, sigma square root pi a. So, relatively easy. Here it's called y in this function. So K1c equals a geometric factor, y times the external effort, the applied stress, times square root pi, and the crack length. So this is what we know from the theory with some geometry and safety factor. And then we have to do experiments in the lab to get the K's. So the K1c have to be determined. We do computer simulations in the lab, in the design. The guy who designs the airplane, the guy who designs some specific parts for the plane or for the car or for the train or for the skyscraper. So this is done in computers, finite element simulations, for example. And then, of course, under which working conditions do we use it? Is the airplane just sitting there and standing, then it's not so much happening? Or is it heavily loaded, full tanked, full of passengers, flying in the air, in thunderstorms where the wings go up and down like flip-flop, flip-flop, flip-flop? So these are the working conditions. And now, of course, I mentioned already, we have to track. We have to track the crack lengths after, let's say, after a certain number of flights in the airplane. Everything, the critical parts, they have to be checked. They have to be checked by visual inspection, by ultrasound inspection. And if you find cracks, then you determine, okay, they're underneath a certain length limit, or they surpass the length limit here and may lead to a crack. And then, of course, with the safety factor, you replace the part. You have to repair it. The airplane is designed with cracks. The engine, high temperature materials, they have creep. Later on this lecture, we will talk about creep. This is where the materials becomes longer at high temperatures in the turbine, and the turbine blade does not last forever. After some lifetime operating hours, it will lead to failure. So we have to design when the machine has to be serviced, when these parts have to be replaced. And the same is for the cracks. So here, the allowed stresses, we can plot that, of course, if we have the length here, allowed defect length, can be a crack, can be a soft inclusion, and then, of course, with the high K1C, we can allow higher stresses than with a low K1C. So this curve is the 1 over square root pi a. Here's an example. So the fracture stresses of a large window glass. You have a big window, then it has a crack in the middle of the length 2a, 200 micrometer. What are the allowed stresses? This one you look up somewhere in your table. This is the crack you want to design. Okay, you say pretty often you want to allow a crack or inclusion or whatever of 200 scratch of 200 micrometers. What is the allowed stress? You can apply, so solve the formula by sigma c, which becomes K1C divided by square root pi a now. So you have all the parameters, all the numbers available, and you get 39 megapascal. So with 39 megapascal or lower than 39 megapascal, you're safe. Then also all these tables and ASM and standards, they have already lists, so you don't need to calculate all that. They have lists for types of cracks, shown here to the left. So we have a central crack, the length is 2a, an infinite plate, like in the window glass. We just did this exercise. We may have the crack at the edge. So this is the crack here at the edge, not in the center. Length is a in the semi-infinite plate. Then we have the K1C becomes 1.12 times the one above. Or we have a penny shape cracked, becomes 2 sigma square root a over pi, so a different form. That's because it is kind of a two-dimensional constraint. We have a center crack, so penny shape is you have inclusion inside, limited in 2 dimensions. Center crack 2a in length. I rush on because there will be another figure on this. As I say, these slides are just collection of figures and stories. So again, we have typical representation, which you see often in presentations and in the design studies of fracture toughness. The metals here to the top. Then we have the polymers somewhere, engineering polymers, they're a little higher. We have the ceramics and then the rocks here, so these are earth materials. Wood is here, PVC, nylon, and what do we have here? So we have diamond here. Has a high strength, we know, it's very hard. Aluminium oxide is very hard, but the fracture toughness is not so high as for the metals, because there's no plastic deformation. Once you have crack initiation, then the crack just grows. Another of these tables, I'll let you go through it. Also look up here, engineeringlibrary.org. Here again, the table I showed a few slides ago. I don't want to go through that because it's here again. So we have the mode 1 stress intensity, K1, associated with short cracks. So in all the cases, the crack length C now, which was A before, is much smaller than the width here of that material. And then we have, well, before it was said in words, but here we have it now in pictures depicted. So the crack in the center, the crack at the edge. This may be a penny shaped, so where it's in 2 dimensions, in the plane, yeah, perpendicular to the stress. Here we have a crack which comes from the bottom. Here's a penny shape. This is a penny shape. Internal penny shapes. So various situations, and according to these situations you get the formula in those tables here, and you just apply them. Oh, here come the nice numbers. Okay, I didn't know. I don't make that fancy slides that other people do. I got these slides here. Great. So here we have all the stress intensity factors for those situations. Namely just the sigma square root pi c, the 1.12 times that one, and here, what is the p? There's a little p here. It has some stresses, maybe some stress concentration. Here it comes from the bottom, and here's the penny shape. So the penny shape has this one. Again, for example, there's this one also, thin section, plane stress, double slit beam, various geometries. I cannot go through all of them. If you want to read more, and if you really need to design something, so that's the point. When you come to the lab, when you come to my lab, you have to design something. Yeah, that's very typical. We have to build up machinery. We have to build up sample environment when we want to study the material. And maybe we want to crack the material. I want to crack material with fatigue. We have projects on that, and we have upcoming graduate students on that. So then we have to design something, and you have to find the numbers. And there's, for example, numbers and a little bit of introduction, handbook of stress intensity factor, stress analysis of cracks handbook, and so on. You can read to the table. I added this here today, Engineering Library Online. As said at the beginning of the course, Internet is a very big help. And of course, there are calculation methods, analytical methods. We introduced a few analytical methods here, but this is very limited. Other more complex situations are done in the computer by finite element analysis. This is very powerful, and the boundary value methods. Here, one more example. What happens if you have this inclusion, which is round, and then you have a crack here and a crack there? Let's make it symmetric. Then we can say this round inclusion equals, with a small crack there, equals this, which is just a round inclusion. And there we know already the stress concentration is 3 times the sigma which has been applied in the far field. We have done that before together, plus the initiation or the crack at the straight surface, which I told you the beta is 1.12, just 2 slides before. So we have 3 times the stress concentration, so it becomes 3 times 1.12 equals 3.36 for the stress intensity factor K1. These are now pictures for finite element analysis. I cannot go through them because I'm not a specialist. Atrash Fuad, who has made this slide, he was a specialist on finite element analysis. So I refer to those kind of people if you want to know more on those examples. Thank you very much. This concludes the theory and introduction into fracture cracking. Next time we talk about the statistics on cracking, namely the Weber statistics, and then we come to other mechanisms of failure like fatigue, creep, and at the end of the course, thin films. Thank you very much.